Hello, today we're going to get started with energy. So we just wrapped up force and on the last unit and then work in the last section here. So we are going to start combining some of that into energy. So we're going to talk about different types of energy, be able to differentiate between them, and then calculate different variables using those formulas. So we'll start with kinetic energy. We know that this is the energy of an object in motion, which that's a pretty basic concept. So kinetic energy can be anything that is moving. The more mass it has, the more kinetic energy it will have. That's also true for velocity. So if you increase the velocity of something, it also has more kinetic energy. This has to do with inertia as well, which we've kind of touched on a little bit already before. So if you have, let's say you have a truck driving down the highway and it has a huge mass versus your car, and you're both driving the same speed, the truck's going to have a lot more kinetic energy because it has more mass, which is related to inertia. So this is a formula we're going to use down here written in red. It's going to be capital K, capital E equal to 1/2 times mv squared. Okay, so we're going to have kinetic energy is going to be 1/2 times the mass in kilograms times the velocity in meters per second squared. The unit for kinetic energy is going to be joule. It's a scalar quantity, so it does not have a direction associated with it, just the value in the unit. So when you calculate these, it will just be the number with a J behind it for joule. That should sound familiar, the joules anyway, because we did use that for work, and I'll explain why in a second. So a quick example here for the kinetic energy formula. John ran 18 kilometers in 1 hour. If his kinetic energy was 694 joules, what was his mass? So we are given quite a bit of information here, and we are trying to find its mass. So in order to have mass, if we're looking at a formula, we have to have the kinetic energy and the velocity. We do not know its velocity, but we can calculate it. So if you think back to a couple units ago when we had velocity, it's going to be the distance divided by the time. Velocity does need to be in meters per second. So this was first calculated in kilometers per hour because we are given kilometers and hours. But once we find it in kilometers per hour, we need to convert it into meters per second. So this is already done here. We end up with a velocity of 5.0 meters per second. Now I have what I need to substitute that into my formula to solve for mass. So I'm going to substitute in the kinetic energy of 694 joules, set that equal to 1/2 times mass times the velocity of 5 squared. When we solve this, it should be 55.5 kilograms. So this is useful because you're able to find like a few different things here. You could solve something's velocity. You could see how fast something was going based off of it, the energy that was being created in its mass. You could find the amount of energy, which is then related to the work. So these are pretty useful, and this will be useful in the roller coaster project we have coming up. So if you have a reminder here that these are your formulas for work, and then this last formula here, the VF2, that one's from a couple chapters ago when we were talking about two-dimensional motion. So if you have your work is your force times the distance, work is also mass times acceleration, and then at the end here we have the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance. So if you look at those three formulas in gray, you can see that there's some commonalities between them. The last two both share acceleration, and that means that we could rearrange the very last equation and have it set equal to A, and then take what it's set equal to and substitute that into our middle formula. So that's what we did here in the purple at the bottom. So we are going to basically derive our own formula to solve for work based off of what we have. So in this case, if you don't know the force or the distance, or if you don't know the acceleration, you can use the final and initial velocities to solve for that instead. So the work kinetic energy theorem explains that work and kinetic energy for a system should be equal. So the net work done by all forces acting on an object is going to be equal to the change in the object's kinetic energy. So if like in this example, if you have a hammer and you're trying to like do that thing at the carnival where you slam it and you ring the bell, you are moving the hammer, which is creating kinetic energy, and then the hammer is hitting the board at the bottom and transferring its energy into this board. So it is applying a force to the board downward. The board moves downward and then triggers a simple lever system here to make the the puck on the other side shoot up and hit the bell and ring the bell. So you are transferring that kinetic energy straight into a force that's being applied, and you're going to end up with the same amount of work as there was kinetic energy because you're applying a force over a distance. So those are equal, and that's why they share the same unit. They both have the unit of joules, both work and kinetic energy, because it's going to be newtons times meters. That's that unit. So you're going to have force times your distance. Example of this, we have Ellie and Leah are pushing a 90-kilogram cart across the field. After it is pushed a distance of 6 meters, starting from rest, its speed is 10 meters per second. What is the magnitude of the net force on the cart? So if you have all of this information, we're trying to find the net force. We know that we're going to have to eventually use this red formula because it has force in it, and the purple one does not. So we are going to first use the purple formula and solve for work, and then we can come back in and substitute work into the red formula with the distance that's given to solve for the force. You could also derive your own formula using these two if you would like. So here we're going to do it the method that I described. So we're going to substitute in the mass, which is in kilograms. We're going to have that multiplied with the final velocity squared minus the initial velocity squared, all divided by 2. That gives us work of 4,500 joules. Now we can substitute 4,500 joules of work into the red formula, set that equal to the force times the distance, which is 6 meters, to solve an overall force of 750 newtons being applied. Potential energy, on the other hand, is the energy of an object that is stationary, so something that is sitting still. A lot of times this has to do with gravitational potential energy, but there's also elastic potential energy, kind of depending on the situation and what you are trying to solve. So if I have potential energy of gravity, so gravitational potential energy, that is going to be PE with a subscript of G to designate that it's talking about gravity. And that's set equal to the mass times the gravity times height. So if I have the acceleration due to gravity. So if I know the mass of the object, I know how high the object is. If we're on Earth, we know the acceleration due to gravity. You can multiply those values to figure out the potential energy of that object. So here you have this picture at the bottom here in Bubble Rock in Acadia National Park in Maine, and this person is pretending to push this rock off the edge of the cliff, right? So this is a huge rock, probably several tons, and you could calculate its potential energy. Like, what is its potential energy just sitting at the top of this cliff precariously? On the other side, you have elastic potential energy. So this is going to be your stored energy in any deformed elastic object. So anything that would snap back to its original shape, or at least attempt to do so, could have elastic potential energy. So if I took like my pen and I bent it a little bit, the pen is going to immediately return to its original shape as soon as I let go. If I have a rubber band and I like launch it at someone across the room, when I stretch it out, it has elastic potential energy because it has a stored amount of energy that it's going to use to reform its original shape. So the formula for this one is going to be PE with an elastic as a subscript, is equal to 1/2 kx squared. So in this formula, k is our spring constant, which we talked about last unit. So we know how to find the spring constant. We know that spring constants are things that exist if we know what type of materials we're using. So you can calculate it. Sometimes it'll be given. And then x is going to be the distance that object is stretched or compressed from its relaxed state. So some examples of that, the first one here with the spring in the middle here. The first one's just sitting in its normal state, but then you can stretch your spring and cause elastic potential energy, or you could also compress it, because in either state they want to return to their normal state. So example 3 is going to be a spring with a spring constant of 3.5 Newton meters has a relaxed length of 2 meters. When fully stretched by a hanging mass, the length is 4.2 meters. Calculate the elastic potential energy stored in the spring. So in this spring, when it is stretched to this distance, what is the potential energy? So we're given a lot of things here. We know the spring constant is 3.5. we know the two different positions that it was in, so we would have to find the difference in those to figure out the distance it was deformed. And then we need to find out what the potential energy is. So we are going to insert those into this formula. So when we do that, we're going to have potential energy, elastic energy is going to be equal to 1/2 times your spring constant times the amount of distance that it was deformed squared. And then you would solve for that to get 8.5 joules of potential energy. Conservation of energy is going to be the last thing we're going to talk about today. So we're going to talk about which conservation of identify situations in which conservation of mechanical energy is valid. Talk about the forms that conserved energy can take, and then we'll solve a few problems for that. So for your conserved quantities, just means that it is staying consistent, okay? So if you have conserved quantities of energy in different states, it means that you are balancing that out. So your total energy should always be a sum of your potential and kinetic energy. So it can change forms, but you'll always have the same amount. So it's no different than the law of conservation of mass. The law of conservation of energy is also something that is true. So if you lose a certain amount of energy, it's not actually going anywhere. You're just changing it into a different form. Okay, so if you have like light energy, eventually turns into heat energy, and then that can turn into some other type of energy. So here with this example of these glasses, if you have a glass that is full and has water in it, it doesn't matter if you shatter the glass on the floor, you're still going to have the same amount of glass, basically. Down here is another good example. So if you're looking at this roller coaster at the bottom, at point A, and then it kind of like pulls you through the roller coaster and shows you different points, notice that the total mechanical energy, the TME, is same throughout, but the kinetic and the potential energy will change. So they always balance each other out though. So if it appears that there is no kinetic energy, that means that it is all potential energy. And then as it starts to move throughout the roller coaster, the amount of kinetic and potential energy will change a little bit depending on its position and its velocity. So mechanical energy is going to be the sum of kinetic energy and all forms of potential energy. Okay, so mechanical energy is all the energy involved. In the absence of friction, total mechanical energy will be conserved. Okay, so as long as you're not changing some of that into a different type of energy, like heat energy or electrical energy or something like that, it will always be conserved. So if you look at this like little graphic organizer at the bottom, on the left-hand side, it gives us mechanical energy. So kinetic energy is obviously mechanical energy, and then potential energy, it could be made up of elastic or gravitational. Those things all make up mechanical. If you have somehow converted that into a different type of energy, like nuclear energy, chemical energy, electrical energy, then they will not be equal. Your initial and final mechanical energies would not be equal. So if you look at these two photos on the side, here you have a pendulum, and you have kind of a diagram here of where the potential energy is great and then where the kinetic energy is great. So if you compare that to the graph beneath it, they are exactly opposite, but you have the same amount of energy throughout the whole thing. So even though the kinetic energy is highest in the center, that just means that the potential energy is the lowest and vice versa. So with mechanical energy, your mathematical expression for this is going to be that 1/2 mv squared plus mgh is equal to 1/2 mv squared plus mgh. So you have your initial is set equal to your final. So if you look at these formulas and maybe go back to the other formulas for potential energy and kinetic energy, you can see that this is going to be the potential energy plus the mechanical energy, potential energy plus the kinetic energy set of the initial form set equal to the same for the final form. So if other forces are involved, the initial and final can be added to both sides of this equation. So if some variables are not needed, they can be taken out on both sides. So if you don't need mass, you could remove mass from all parts of the equation. So up in this top corner, we have a diagram here of a skier skiing up a hill. It shows you kind of where the kinetic energy is lost and potential energy is gained, and then that's represented by the size of the values there. So just another example. So again, just to summarize, mechanical energy is conserved in the absence of friction, and mechanical energy is not conserved where friction is involved. All right, so here's an example. We have a person jumping off of a 10-meter high diving board with an initial upward speed of 1.5 meters per second. What was the person's speed as they struck the water? So what we're given, we already know that gravity is 9.81. So we know that that would be the g portion of this formula. We know the initial height is 10 meters. The final height is going to be 0 meters because that 0 would be where they hit the water. The initial velocity is 1.5 meters per second, and we don't know the final velocity yet. So we're going to use our mechanical energy formula. In this case, we don't have mass, we don't need mass, so we're going to remove mass from all parts of the equation, which leaves us with the blue equation here. So we're going to start substituting in these values. So we have the initial velocity, we're going to sub that in, plus gravity times the initial height, set equal to 1/2 the final velocity squared, plus gravity times the final height. So when we simplify this is what we end up with. You would need to then get the square root of both sides. From this part, you would need to multiply both sides by 2 to get rid of that 1/2 and then get the square root of both sides. So what we would end up with here is that the final velocity is 14.1 meters per second. So the next section we'll talk about is power. We'll touch back on that tomorrow. Today we're just going to focus on the different types of energy, so potential, kinetic, and mechanical energy. So you guys do have some practice problems to get done. Please let me know if you have any questions, and I will talk to you guys next time.